dive into network slicing aspect of it. So in this webinar, I'm planning to uh, cover some sort of introduction into network slicing and network 5G network architecture and components and how slicing can be implemented in a telco network. And then we will go through what is slicing and the difference between physical, logical slicing and different aspects of that. And then we will cover different slicing requirements and different frameworks and the standard specifications. And then we will cover how we could allocate different physical and logical resources in a telecom network, including radio, transport, and core. And then we will go through some of the standard bodies and what they are doing and all that stuff and what's the future. And integrating network slicing principles with other standards like CNFE MANO and also cloud native infrastructure. And then we will cover its future trends and some practical aspects and difficulties that we face when we implement network slicing in telco network. So just give you an idea. So uh, what it means by network slicing is, I mean, if you take a typical telecom network, the telecom network would consist of mainly three components: a radio access network, transport network, and a core network. Okay. And so what it means by network slicing, because network slicing itself is sort of a term coined by, I mean, like there are a lot of definitions to it, and predominantly governed by organizations like 3GPP, third generation partnership projects. So the definition of a network slice is to be able to create some sort of a, I mean, like allocate network resources, I mean, like virtual, I mean, like network resources or certain network capabilities in a physical network infrastructure. So it should be able to create logical networks on top of physical network infrastructure. So if you look at current telecom networks, we are not used to a concept similar to this. So we will go through that one in the next slide as well. So the main idea behind network slicing is being able to cater to different service level objectives end to end. For an example, let's say you have some sort of a requirement for latency and some requirement for broadband, in-house mobile broadband, some requirement for massive machine type communication. So you should be able to allocate virtual resources, logical resources, and the network end to end. Okay. So that's the main idea behind network slicing. And if you look at the old generations of telecom networks, on the left side, you can see uh, on the left side, you can see LTE network. So predominantly LTE network would consist of an EU-RAN, radio access network, then EU packet core, and in between you can have transport network, and you can connect to multiple packet data networks. It could be internet, it could be some sort of an IMS, it could be some sort of a business to business scenario. But in the previous generations, we did not have a concept similar to network slicing, because we had the idea of, let's say, EPS bearers and allocating different QoS flows and VLANs and also layer 3 VPNs, layer 2 VPNs and VRFs and all those concepts. But we did not have some similar idea like allocating logical resources for different types of business requirements. That means uh, in a hard slicing mechanism, or maybe it could be a soft slicing mechanism, but we did not have a similar uh, implementation in the previous generations. But in later early 3GPP 13 release, pre-releases, and also in 14, we used to have concepts of dedicated core networks, but that uh, but apart from that, there was no idea similar to network slicing. So we will go through those things in detail because there are a lot of technical terms associated with network slicing. I will explain them one by one in the upcoming slides. So the idea here is to be able to connect to multiple uh, logical networks through a telecom network and sharing those resources. Okay. So this is sort of a high-level overview. So on the top, you can see different industry verticals. It could be manufacturing, it could be energy, it could be finance, anything like that. So you can have different industry verticals, and then the network operator should be able to allocate uh, radio resources and transport network resources and uh, core network resources accordingly. So there could be a lot of planes. I mean, this is sort of a diagram I have taken from ONAP. So you can have some sort of a management plane to control all those network slices. So we will go through them in detail when we explain topics in detail in the upcoming slides. So you need to have some sort of end-to-end network slice management uh, component, and in network slicing terms, we call it network slice management function. So we will explain them in later, and uh, and then we can have slicing capabilities in the data plane itself, and also in the control plane itself, and also we can take slicing to the management plane itself. Okay, so this is sort of a very broad view of network slicing and where it is from technology perspective. So you can see in the quadrant itself, I mean, like on the left side, you can see OSS domain, and from network slice management perspective, and what kind of things need to happen, and where we are in terms of 3GPP releases and all that. On the right side, you can see core network and radio network and transport network. So we will go through some of those domains in detail, and I will cover and where we are, and what kind of features that we need to have in a telecom network. So the main, I mean, the reason why I actually wanted to do sort of a separate webinar on network slicing itself is because uh, network slicing is the main revenue driver of 5G telecom deployments, because it's similar to what we used to see in 3G. Usually, I mean, third generation, I mean, 3G was released back in early 2000s, but until 2007, we did not have a very strong business case, okay, because some sort of a revenue drivers telcos to invest in. And and if you take 5G itself, and I mean, the kind of investment that we have to do to build 5G radio networks, transport networks, and core networks, and that revenue has to be, I mean, like compensated or maybe recovered some way. And I mean, like the investment that the telcos make, and then then if you take the revenue of most of the telco operators now, it's the average revenue per user is quite flat, and there's no new revenue growth mechanisms to improve. I mean, improve the revenue and all that. So predominantly 5G will be a business to business. Uh, uh, I mean, revenue stream. I mean, so that's why we need network slicing to be able to cater and provide different SLAs to different businesses, and to find new revenue streams. So GSMA is another standard organization. They have also defined the different types of network slicing requirements. And one aspect is we can uh, explain network slicing requirements from performance perspective when you build a network slice, and it could be throughput requirement, it could be latency requirement, it could be functional requirement, or it could be an operational requirement. So I will explain them in later, I mean, in detail in later slides. And the other thing is when we take network slicing, there are multiple ways that we can do it, and we don't definitely need to have build an end-to-end network to cater network slicing requirements. And we can uh, enable slicing capabilities in radio and transport network, radio and core network, and also in the transport network, because it will take some time to come up with new standards to be able to deploy slicing. So I will skip this slide, and we'll get into the details. Okay. Okay. So uh, here you can see certain, I mean, like standards related to network slicing. So predominantly network slicing related standards are governed by 3GPP, and there are different working groups, SA2 and SA5. SA5 is predominantly related to network slice management and architecture. There are RAN network groups, RAN working on slicing, and those specifications are mostly related to radio and core network. And if you take transport network, telco transport network, so the standards are mainly driven by IETF. So there's no direct involvement from 3GPP. So there are frameworks like IETF Act 10, and also network size management frameworks are already defined, and IETF drafts are already going on. in that domain, and also adopting Sigma routing, MPLS, Sigma routing V6, and all those things are governed by IETF standard. That's something you should clearly understand, because if you take slicing itself, there are a lot of standards bodies working, and currently there's no overlooking body into every aspect of network slicing. And also Etsy is also involved, and Etsy CSM, Zero Touch Service Management Framework, is also there to define management interfaces and specification related to that. And IEEE is also involved in terms of time-sensitive networking related to standards. So if you take network slicing itself and predominantly in the 5G front haul, then we need standards like TSN, and how we can do scheduling and preemptions and frame preemption and all those things. So they are defined through IEEE 8021 and 8021 CM profiles. And Flex Ethernet has an involvement, and OIF predominantly optical interconnecting forum. So there's a standard called Flex Ethernet, and it's a sort of a TDM-like technology we explained in the last webinar on transport network. And also Metro Ethernet Forum has a specification called Metro Ethernet MEF 84. So, and also especially GSMA. They have a couple of documents they have released. One is NG 135, so it's about end-to-end network slicing requirements, and NG 116, which is very important in terms of network slice templating and all that stuff. So it's a sort of a collaboration between different standard bodies to realize network slicing as a whole. So there's also collaboration between different standard organization and how we can achieve slicing end to end. Okay, if you take a typical network slice itself, then there are multiple phases. This is sort of a high level overview, because there are standards to define how we can create network slices. And typically, if you want to create a network slice, there has to be some sort of a phase where you should be able to prepare a network slice and do the modeling and template. And so from application perspective, there has to be some sort of an network slice design studio where a telco operator could design slice templates, and according to that should be able to create the network slice. Then the other aspect is network slice creation. So we can call it NSI instantiation, and and the other aspect is network slice operation. Once you create a network slice, then you should be able to operate that. So network slice activation and monitoring, scaling, and all those things are handled in that operation. And then the network slice termination. So like that, there are a lot of phases to a network slice. I mean, if you spin up a network slice, then it's like managing a virtual network function, similar to that network or virtual VNF. And because in previous slides I did not explain those terms, so this is sort of an explanation what those terms mean. So if you are talking about network slice, then there are two main terms that you need to understand. One is network slice instance. So we use the term network slice instance to denote network slice that we create end to end. That means core network, transport network, and access network. So if we create a network slice, we use the term NSI. A network slice subnet instance is that when you have, I mean, like for an example, in the radio access network. So if you create sort of a slice, then we use the term NSSI, or network slice subnet instance. Same way in the transport network or core network, uh, based on the domain that you're talking about. So we can allocate a network slice subnet instance to that. So uh, and network slice selection assistance information, NSSAI, and NSSAI means that's the uh, th- that's what I mean. Like, we use the NSSAI or single NSSAI to denote or identify a specific network slice, right? So we will explain that in the upcoming slides. So so this is how it look like, and so you can have some sort of a end-to-end network slice end to end. And so we use the term NSI, and then each domain, RAN domain, transport domain, and core network domain, you can have respective NSSI network slicing subnet instances. And access network, it could be transport network, it could be core network like that. So each NSSAI can define the requirements, and also network slice instance management, network slice subnet management, the respective domain. Okay. So this is sort of a high level overview how we do the slice management. So this is defined by 3GPP itself. So we have on the top we have communications service instances. So we use the term communication service instance to indicate some sort of, let's say you are a customer, you want to create some sort of end-to-end latency sensitive slice, or maybe some sort of a slice for massive machine type communication requirement. Then so that creation, or the logical creation, can be denoted through the term communication service instance. So there has to be some sort of an API call that should be able to instantiate NSI or network slice instance down below. And so on the right side, you can see different management functions related to each and respective domain. And so for communication service instance, then you can have some sort of a network function called CSMF. So it's a 3GPP defined, and a network slice management function which would manage a network slice instance that you create. And then for respective network slice subnet instances, there are network slice management functions. So for core network, we can call it CNNSSMF. Okay, that means the core network slice service management function. So this is the architecture, though, and the nomenclature related to network slicing. So I previously explained network slice selection assistant information, so which is used to denote a network slice that we create. So typically a user equipment could have up to 8 network slices, and 3GPP has defined like if you take network slice selection assistant information, so there are two parts to a network slice selection assistant information. One part is a slice service type, and the other part is slice differentiator. And the slice service type is an 8-bit value that you can use, and that you can, in 3GPP, there are, like from 0 to 127 slice service types are already standardized, are already reserved, and out of that, around 5 are already defined. So you cannot use those slice service type values if you intend to use it for a different purpose, or for your own custom requirements. And the SST values from 128 to 255 are free to use for operator specific requirements. And the other part is a slice differentiator, or DS part, so which we can use to differentiate your own slice. Let's say you create an enhanced mobile broadband slice for a specific customer, then the differentiation would happen at the DS level. Okay. Uh, so this is sort of a elaborated view how that field looks like. So you have slice service type, and then you can have 3GPP defined slices up to 127, number 127, and first 5 slices are already defined. And the other side, slice differentiator, can be customized based on your requirement. Let's say you are providing some sort of enhanced mobile broadband service to some sort of a BFSI customer or something like that. Then you can categorize them using this service, and you can do the custom identification of the rest of the bits, and then you can indicate the slice priority and all those fields in the slice differentiator field itself. So this is how it looks like. And the other most important thing when you create a network slice is that you should be able to template or build templates around indicate network slice, and the configuration related to that also. So there are a few standards defined by GSMA, and also by 3GPP in technical specifications. One term is very common term is GST, generic service template. So this is what GST means is it's sort of an attribute that can characterize the type of the network slice. That means uh, one or more network slice instances can be created out of the same GST. So when you define certain values for a network, for a GST, then we can call it a network slice type. So which is not shown over here, but 3G, GSMA has defined that term. And so then network slice type or nest can contain all that information related to, let's say, throughput or maybe latency and all those things. And also there are a few profiles defined by 3GPP itself. So this is a sort of slide that I have taken from ONAP. So ONAP has their own terminology related to network size templating and how they can build network size templates. And there's some term called service profile and slice profile and in 3GPP. So we should be able to do that mapping from GST to size, service profile and slice profile. This is sort of an overview how the GST looks like. So GST has certain attributes, and so there could be mandatory, there could be conditional, it could be optional attributes, and then there are different attributes for a generic service template. That means it could be performance based, it could be based on scalability. So there are a lot of network slice GST related attributes, and which you can use for to create a nest. That means you define the numbers. Okay, that means a nest is GST with numbers. And so let's say you want to define the availability of a network slice. Let's say you want to give some numbers for delay tolerance or maximum throughput that you can download and upload, or maybe maximum number of UEs that could connect to a certain network slice and all that. So they are defined uh, in the GST attributes field, and then you can use and create some sort of a nest out of that GST. So this is over here, what you can see over here as NSC means network size customer, consumer. Then you have different use cases, then you have the requirement, then you will create a GST out of those requirements according to GSMA. And then once you provide those numbers, then you can create a nest out of that. And that nest can be used to uh, translate your requirements into service profiles, and also uh, service profiles uh, from 3GPP. Okay, so there are a couple of standards as well, like 3GPP-TS 22.261 and 3GPP-TS 22.104. So they define size service type and the service type and service type. And so another aspect that we need to understand, because we in the previous slides we talked about how we can model a network size using different, different templates, and how we can do the modeling and all that stuff. And when it comes to network slices and slice control, then that control would happen at the core network itself. So there are a lot of, like in the previous webinar, we went through the core network aspect of as well, like core network SBA architecture. And in the core network, there are multiple network slice functions, network slicing related functions. The main function is network slice selection function, and this would define the, mainly uh, mainly used to network slice selection, AMF selection. Let's say an AMF wants to know about the allowed network size network slices, allowed NSSAIs, then you can get that information from network size selection function. And also if the AMF is not capable of uh, uh, providing services to a certain specific network slice, then the NSSF would select the required AMF uh, for the control plane functions, control plane related functions of 5G SA core. And there are new network functions also defined by 3GPP. One is network size authentication and authorization function, and which came in release 16, and also a network size admission control function. So network size authentication and authorization function is predominantly is a AAA server. And AAA, if the AAA server belongs to a third party, then AAAs will access via a AAA proxy. And the other thing is network size admission control or access control function is something that monitors and controls the number of registered UEs, user equipment, the number of PDU sessions per network slice. So with an SSEF, usually operators can enforce quotas on individual slices and making sure the signaling traffic and packet flows do not exceed the maximum slice load. And and the other network function is network data analytics function, which is not directly related to network slicing, but which was defined in 3GPP release 16. And it provide SNSSAI analytics and also so it's like the entry point for AI related task in the 5G core network itself. And the network data analytic function can query for slice load levels, slice QoE measurements, and subscribe to slice specific notifications and provide periodic updates or anomaly alerts and all that stuff. And so in here, you can see that network size selection function itself can consume to network data analytics function, and also PCF can subscribe to network data analytic function, and AMF can take information from an SSF. So those are the main network functions in the 5G core network that would uh, support network slicing control part in a telecom core network. So here you can see how network slicing can interact with HC NFV MANO architecture. So if you are not quite familiar with HC NFV MANO, I will cover that in the upcoming webinar when we cover NFV and also cloud native principles and how they can affect telecom networks. But for the sake of understanding, usually telecom networks implementing virtual, I mean, like building virtual infrastructure, have a virtual infrastructure manager. Let's say it could be OpenStack or something like that. Then you need to have some sort of a VNF manager. So that will take care of different VNFCs or virtual machines. And then on top of that, you can have a network function NFV orchestrator that will orchestrate a different virtual network function components. That means different VNFs, and will stitch together those VNFs. So in network slicing terminology, uh, so the NFV O will interact with the network size selection management function. So this is because NFV infrastructure, NFV MANO architecture or infrastructure is considered as a subdomain. So network size selection management functions, whatever the application that you have from that specific vendor, should interact with the NFVO. Or if it is a cloud native infrastructure, then you will have to interact with the container orchestrator, or maybe some sort of cluster manager, whatever. So the VNF manager will definitely will interact with the network function management function. Typically, over here, it was an EMS or NMS system managing that specific PNF or VNF. So network slice management function will be on the top. Will be managing the entire network slice management functions. It could be cloud native infrastructure, it could be core network, it could be transport, it could be radio access network. So on top of that, you can have some sort of a customer CSMF, okay, communication service management function. Okay. So over here, this is sort of a representation how cloud native infrastructure could be managed. I mean, like can be used to provide slicing. That means provide a certain virtual compute memory and uh, resources, storage resources. And so if you have different clouds at the central location, or maybe at the edge location, or maybe radio access network location, then we should be able to spin up certain user plane functions and allocate certain network resources, network compute storage resources to different slices according to the requirements for different slice requirement for different network slice instances. So this is sort of an overall overview. I have not put in the transport network in detail over here, but you can see there are service orchestrations on top of everything. So that would take care of service assurance, service fulfillment, and also some customer portals and all that stuff. And typically OSS or BSS system. And Then you can have some sort of a end-to-end network orchestration system. And so usually these OSS BSS portals can contain a CSMF function, communication service management function, which we explained in previous slides. And then you can have some sort of end-to-end network orchestrator, and so that we can use the term NSMF to denote that one. And then for radio access network, transport network, and core network, you can have different network size selection management functions, and that will take care of slicing. That means, for an example, RAN slice controller, or maybe if it is an open RAN deployment, it could be a radio RAN intelligent controller. If it is a transport network, it could be path computation element or some certain SDN controller. If it is a core network, then you can have SDN controllers for your NFV infrastructure, then some sort of NFVO, and then some sort of core network slice controller that would take care of um, slicing allocations. That means spinning up new container network functions. Most of the time, we deploy core networks as cloud native network functions. That means because of that, we should be able to spin up those network functions according to the load requirements and all that stuff. And over here, you can notice that we can share a common DU pool, and then I mean, like based on I mean, like in the previous slide, I also explained sometimes you can share a certain DU pool, DU resources, and then you can connect to multiple user plane functions. We will explain that when I go through the RAN slicing slide. And you can connect to different user plane functions, and then at the core network locations. And according to your requirement, you can also allocate different session management functions, whether you require it or not. And we'll come to transport network slicing. So in the transport network itself, because in the previous slides I explained that transport network slicing is not directly governed by 3GPP standards. 3GPP has standards for radio access network in the RAN group and also SA group for a core network. But for transport network, it's predominantly by IETF, and they are not closely aligned sometimes, and sometimes there is collaboration, but currently no IETF proper RFCs is released, or set of RFCs released to uh, uh, give some sort of a network size management and also size creation and all those things. Still, that work is ongoing, but for data plane and control plane related stuff, mainly related to segment routing and all the stuff, they are already finalized to a certain extent. So what you can see over here is that you can have different networks slice, single network size selection assistant information requirement. That means you want to create some sort of network slice from the core radio network, then you have certain requirement in the core network, then there those are subnet instances. Then you should be able to stitch them through the transport network. So mainly transport network could consist of metro access aggregation routers, core networks, and a lot of IP/MPLS routers and OTN equipment or optical network equipment. Then the requirement is to be able to create an edge from maybe from cell side gateway or maybe front haul gateway towards the provider edge of the transport network. So to do that, there are multiple ways that you can do network slicing in the transport network. And in the previous webinar, we covered transport network aspect of transport network evolution and how 5G evolution could also change the transport network and in different aspects. So if you want to cater slicing, let's say provide certain SLAs, service level objectives, cater service level objectives in the transport network, let's say latency related or mobile broadband related, then there are multiple ways you can do that through one is soft slicing, the other one is hard slicing. And the soft slicing, you can use segment routing, TE or SRMPLS, segment routing MPLS and SRTE. Then also it's based on IPv6 data plan. Then we can go with SRv6 TE, and also we can use flexible algorithms. And that means typically what it means by soft slicing is that you share the resources, network resources, instead of purely dedicating a certain slice or network resources for a specific slice requirements. That means you can use it based on the demand. So it's not like dedicated virtual resource that you create end to end. But in hard slicing, you will be allocating dedicated resources. For an example, if you use Flex Ethernet, then it's more like a TDM technique where you would render certain bandwidth calendars and all this stuff to carry network traffic end to end. And also you can also do virtual network resource sharing. Let's say you run some sort of a network operating system on top of some sort of hardware, then you should be able to isolate network network operating systems control plane itself to allocate certain network resources for different types of requirements. So that aspect is also there, so that you can take it under hard slicing. So I will go through briefly on SR MPLS and SR360 in the upcoming slides briefly, because we covered that one in previous webinar. So on the left side, you can see how it looks like. And so for core network, you can have an SSMF like that. The transport network could have that network size management function that could be implemented anywhere. It depends on the vendor, because based on the vendor implementation, how we can implement it could differ. So it's not, I mean, like, even if you denote it as an SSMF, that doesn't necessarily mean it's a product. It's a sort of a logical abstraction, just to give you an idea of that function. So you can implement it using some sort of a path computation element and on some sort of an orchestration system on top of the transport network. So we can be we can break down a network into network infrastructure layer, and then on top of that, some sort of a network instance layer. That means some sort of a VPN layer, and that's how it looks like. So the three main ways of doing network slicing is one is flexible. That means you'll be allocating different IGP metrics for certain label spaces if you are doing routing. So let's say if you are doing OSPF for an ISS, then you will have different label spaces for different different IGP metrics. So there are flex algos, and then I think can go up to like 255 something flexible algorithms. So based on that IGP metric, you will have different label space, and you can use a label space to put the segment routing label stack. Okay, and even if it is SRMPLS or SRP6. And the other way that you can do soft slicing is using segment routing traffic engineering. That means you will be specifying the path that you want to take end to end from point A to point B. Let's say from CSR to the business, some sort of a provider edge router. And so it's explicitly defined path. So you can use SRT to carry different kinds of traffic on a specific path instead of using RSVPT or MPLS TE. And the other aspect is flexible Ethernet, Flexi Ethernet. That means you'll be inserting some sort of a Flexi shim in between MAC layer and PHY layer. So the Flexi Ethernet can provide you the capability to do channel bonding, subrating, and channelization. We went through all that stuff in detail in the last webinar on transport network. So those are the things that those are the ways that we can do slicing in a typical transport network. So this is sort of hierarchy how things would look like. This is sort of logical representation. So for a microwave domain, if there's some microwave domain, you can have sort of a SDN controller to control the traffic and to do traffic control and steering and all this stuff. So predominantly in the IP domain, you can have some sort of path computation element to do SRPCE, work as an SRPCE, or some sort of a PC to do IP and optical path computation and traffic engineering. And then on the right side, I mean, optic domain is also mentioned over here. So you can have different types of southbound interfaces, usually to collect information from the network itself using, let's say, BGPLS or anything like that. And then to push those policies down using a path computation element protocol, or maybe BGP, or it could be TL1 if it is optical, or it could be SNMP, or whatever. Or you can use a lot of protocols, RESTconf, NetConf. There are a lot of options to do that. On top of that, you can have some sort of an end-to-end controller that could interact with the network size selection management function for the transport network. So that's the typical architecture, how the management would happen when you do network sizing. And before going deeper into 5G core network related slicing, radio network related slicing and all that stuff, I thought of just giving you some sort of a briefing on 5G QoS. I mean, in previous generation, we used to we were used to terms like EPS BRS, default BRS, dedicated BRS in LTE. In 5G, we usually called it uh, I mean, like we call it a PDU session, end-to-end that we create from radio to the core network. And each PDU session we can have. I mean, like in the radio, you have different radio default. I mean, like data radio bearers, and then in the PDU session itself, you can have different QoS flows. I mean, in the previous generation, when we allocate certain QoS level for a EPS bearer or sort of a bearer, and we used to do it for the bearer itself. Let's say if you allocate certain QoS level 5 or something like that, uh, uh, QCI values, then that would apply to the all those sessions, IP sessions that you have inside that bearer. But in 5G, you can allocate different. You can have multiple QoS flows inside the PDU session itself. At the same time, you can map different IP flows into service data flows, and then those service data flows can be mapped to those QoS flows. Likewise. So you get that granularity capabilities. So the how slicing come into the picture is like this, because you can have a PDU session for a specific network. I mean, like you use it, we can use the term SNSSAI, single network size selection assistant information. So what it means is sort of a PDU session that you create, and in the PDU session itself, you can have that granularity to control the keywords levels at the same time, those service data flows, and also map those IP flows into that session. And so when it comes to radio network, there are a lot of aspects that we need to understand how we can do slicing and all that stuff. And we can do slicing using RAN virtualizations. That means we can allocate uh, user plane functions. Let's say in the 5G, we divide radio into G node B into radio unit, distributed unit, and CU unit. And CU itself, central unit, that means where the PDCP, SDEP, and RRC processing will happen. And we can allocate different user planes. Let's say we should be able to spin up CU user planes as we require. Let's say if you want to create an enhanced mobile broadband slice, then if you want to allocate CU user plane to that specific size, then we should be able to do that. So that's what it means by RAN virtualization. The other thing is spectrum allocation. That means you can allocate certain spectrum. Let's say in the 5G new radio itself, we use OFDM based techniques. That means we will use frequency domain and also time domain to carry information. So uh, we can allocate certain frequencies, I mean, like it's already explained shown over here, like different frequencies uh, 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 to carry information related to a specific network slice. Let's say enhanced mobile broadband or ultra reliable low latency related requirement, or maybe some sort of enterprise requirement. So you can carry radio information in that specific site. And we can do slicing using beam allocation itself, like because we'll be working with higher MIMO configuration. That means 16 by 16 MIMO configuration or something like that. So that means we'll be working with massive MIMO radios. In 5G, we will go beyond that. And so we should be able to do beam forming, beam steering, and all that stuff. So we can allocate certain beams per network slice and all that stuff. So we can do that. Not contiguous beams, but beams allocated. I mean, like beams at, uh, uh, I mean, like with some sort of a distance between those beams, right? So let's say, for an example, if you take this beam and this beam, we can allocate it for different network sizes, right, like that. And then numerology is a concept introduced in 5G new radio. It's a new concept that means in 4G we used to have 15 kilohertz subcarrier spacings in the frequency domain, and to do OFDMA, orthogonal frequency division multiplier access. And in 5G we have introduced a new term called numerology. That means you can increase the size of the subcarrier spacing from 15 kilohertz to 30 kilohertz, 60 kilohertz, like that, based on the numerology, that number. So we can change that numerology for different types of network slices that you have. So based using that one, you can allocate radio resources in the AI interface. And then we can change those different QoS policies, because that's why I explained QoS briefly in related to 5G. And then you can do MAC scheduling. That means if you take LTE or 5G protocol stack, we have a layer called MAC. file layer, Mac layer like that. So we can use Mac scheduling. That means whether you do priority queuing or whether you do preemption or something like that, then we can uh, change that based on the requirement that you have. Then the other one is physical resource block allocation. So if you take 5G new radio frame, you have frequency domain, you have time domain. So you can allocate certain physical resource blocks for different network sizes. And also you can use beamforming as I explained previously, and you can change the subcarrier spacing and all those things. So those are the things that you can do typically if you want to do slicing in the radio access network itself. And this is sort of a overview of how I mean, like this is how ORAN architecture would look like. And typically in open radio ORAN architecture, we have CUs and DUs and some sort of a virtualization infrastructure. And also on top of that, you can have some sort of real-time RIC, a non-real-time RIC, radio RAN intelligent controller. So what happens is, I mean, there are a lot of interfaces. That means, or one interface that means that will connect to all those near real-time RIC and control and OCU CP and OCU CP UP and ODU and ORU. So this is an interface management interface that will connect with uh, all those nodes, including the near real-time RIC. So typically what O1 interface would do is it will allocate RRM policy attributes and also provision PRBs or physical resource blocks and split of PRBs among policies and all those things. So that would happen through this O1 interface. And then the O2 interface, it is also very important, that would take care of uh, ORAN functions, example, near real-time RIC, and also how we can allocate user planes when we do network slicing and all that stuff. And so, so if you are deploying ORAN itself, then this is the way that you can do the network slicing. So you need to have some sort of a RAN intelligent controller. So do radio resource management and all those things. We will go through this in really detail when we cover radio access network part in the upcoming webinar. So you will get a better idea what those interfaces are and how you can do scheduling and how you can uh, do radio resource allocations and how the LT frame, new 5G new radio frames look like and all that stuff. Uh, so if you take network slicing itself, then still in deployment perspective, still in early phases, and those are some of those very recent 2023 news headlines. That means related to network size deployments. And for example, Telefonica and Nokia, very recently Nokia did some trial with Singtel, and Telefonica has recently done some network slicing trial. And so like that, there are a lot of early network slice end-to-end network slice trials are already ongoing. The main challenge is you need to have radio network, transport network, and core network readiness to do end-to-end network slicing. So it's a challenging task. One aspect is you need to have software available, and also the currently still we are in phase 3 in network slice specification at 3GPP. So it will take some time until everything is quite ready in RAN and core network as well. But from transport network perspective, there are a lot of drawbacks and a lot of challenges to do sizing. So we're still in early phases, but in next 2 to 3 years, we will be able to see fully slicing capable telecom networks across the globe, so that they would be able to cater into new different business verticals and to bring new revenue streams and all that. And so that's the end of the presentation. So we have come to the end of the network slicing webinar. So if you have any questions related to slicing, then you can ask me.